Right, so we're going to try a little PowerPoint here with basic physics. We're going to actually really just looking at reference frames and the difference between position, distance, scalar and vector quantities, and displacement, those sorts of things. So let's kind of start from the beginning. A frame of reference. A frame of reference basically is the viewpoint that you choose. So what's your directionality, if you will? So for example, north, south, east, west. In terms of a global scale, we use those things as our frame of reference. Don't confuse that with a reference point. Reference point is a singular point for comparison. Now, if I go back to that same global frame of reference, the reference point would be Greenwich, England, where you have the prime meridian, the 0-degree latitude point, and the equator. Those are your zeros. Those are your reference points. That's where, if you're looking at your latitude and longitude, you're looking at those reference points to see where you are amongst your frame of reference. Generally speaking, we might say in physics that a frame of reference would be what direction is positive and what direction is negative, and then reference point would be where's your 0 point, or where you are always comparing where you're going from, what point are you comparing it to. We have scalar and we have vector quantities. Scalar quantity is a quantity that has a magnitude but does not have a direction. Vector is something that has both magnitude and direction. Magnitude meaning how big the thing is. So it's the number associated with it. Direction is going to very often be positive or negative direction. Could be north or south, east, west, that sort of thing. But most often you want to designate it as perhaps positive and negative. That's really the simplest way to do it, and you can apply that in a mathematical quantity. Got a little YouTube-ish video that we may or may not be able to display here. We're going to give this a try.
By the name of Jack. Actually, mathematics. Quantity represented by an arrow is both direction and magnitude. Vector! That's the on committing crimes. Both direction and magnitude.
All right, we got it. You go away. All right, position is a vector to where distance is a scalar. Position is the separation between where you are now and that reference point, where distance is how far did you really go. Distance is probably more comparable to something called displacement. Displacement being the change in position compared to wherever you were before. Now, the difference between displacement and distance is displacement can have a negative value to it, to where distance will not. It's just how far did you go. But displacement actually tells you where you came from and how far you went. So both magnitude and direction. And so it is a vector. Adding vectors, we have a resultant vector. It's the sum of two or more. And so we have a couple of examples here. We have a car. It's going to go, it's 4 kilometers. Goes another 2. The 2 combined, it is going to be 6. Let's go back and look at that again real quick. So in one case, it's going the same direction. It's 6 kilometers is your final position, to where in the second case, they subtract each other out because it's in a negative direction. And so if you notice adding these two vectors together, if we go tip to tail, the tip of one arrow goes to the tail of the next. You start from the beginning, you just work your way out. On a position versus time graph, the x-axis is always going to be time. The y-axis is going to be position, and the slope of the line that is created is going to be the velocity. So from a position versus time graph, find the slope, and that will, at that moment in time, be the value of your velocity. So in the case of this graph here, we have a positive slope. So that means that this vehicle is moving in a positive direction. It is increasing its distance from its zero position in a positive direction as time goes on. So a straight line refers to a constant velocity. If it's a curved line, then that means that there's some sort of acceleration occurring, that the velocity is changing. The slope is rise and run, so it's the change in position or the change in displacement over the change in time. Remember that triangle means change. We have a few different graphs here representing different vehicles. We have a red car, yellow, green, and orange car. So let's look at them. The red car has a straight line starting at 0, so that means at time 0, it is actually already moving. And it's moving in a positive direction when time starts. It has constant velocity, moving in a positive direction. The yellow car starts off virtually at rest and builds up its velocity over time, increasing its displacement per second with each second that goes by. The green car starts at the 15-meter mark, and then after 2 seconds, it's still at the 15-meter mark. It hasn't moved anywhere. So it is actually a velocity of 0. Horizontal line refers to a velocity of 0. A vertical line represents nothing. It's not possible. It's an undefined scenario. So that refers to it's not possible to have an infinite velocity, so you can't have a vertical line. And the orange car has a constant velocity, but it is negative. It is moving in a negative direction. That's all it means. It's just moving in the opposite direction as the red and yellow car. Average velocity. Velocity is change in position over the change in time. So it's the second minus the first position divided by the change in time, the time that is elapsed. Velocity is a vector. Don't forget that. And it is basically just distance over time again. If we can cut the increments of time to as small as we can get, we basically will have an infinitesimal small amount of time, and we're looking at the velocity at that instant in time. So we're not really looking at average so much anymore, but an instantaneous velocity, and those things we'll look at a bit more later. Acceleration is how much you are changing your velocity. Now remember that velocity is how many meters you're going for every second that goes by. 1 second of time goes by, you're going perhaps 5 meters in that time, so that's 5 meters per second. Well, if your acceleration is 5 meters per second squared, that's really 5 meters per second per second. And let's see if I can express that for a second here. Haha. So 5 meters per second, and I'm going to express it this way. 5 meters per second. That means that for every second that goes by, you're changing your velocity by 5 meters per second. And if you can express this in a different way, it is simply going to be 5 meters, and this looks terrible, I know. 5 meters per second squared. Those two values are the same thing, and it simply just means that for every second that goes by, you are changing your velocity by a rate of 5 meters per second. three things that affect velocity, not really acceleration. That shouldn't be like that. But things that change velocity. Speeding up changes your velocity. Slowing down and changing direction. So look at it in terms of a car. What three things can you do to change your velocity or therefore accelerate? If you have an automatic transmission, you have two pedals on the floor. Hitting either one of those two pedals will effectively change your velocity, cause you to accelerate. One is a gas pedal or accelerator pedal, makes you go faster, and that will be an acceleration. Hitting the brake pedal will be an acceleration as well, in the negative direction, at least if you're moving in a positive direction. So brake pedal is an acceleration in the opposite direction that you're moving. Generally, that's going to refer to a negative direction. And then turning that steering wheel is actually an acceleration, because remember, velocity and acceleration, they're all vectors. So if you change your direction, you are accelerating. So again, since velocity is distance over time, we'll go back. We can also replace that change in velocity as a d over t, or x over t if you prefer. They can really be interchangeable and often are, depending on the book. And just like from before, we could get the velocity from the position versus time graph, we can also get acceleration from the velocity graph, from that slope of the line. And so in this case, we have an acceleration graph. The acceleration is 1 meter per second. It is a constant acceleration, and it is in fact increasing speed. And that's that. So hopefully there was a little bit of learning that happened there, and I hope that was helpful. Until next time.